So now we will derive the Fermi-Dirac distribution in the same manner we have done for the Bose-Einstein distribution. So we start with the number of accessible microstates for a Fermi-Dirac system. Number of accessible microstates. Number of accessible microstates for a Fermi-Dirac system, or we can call it as ideal Fermi system, is given by, that we derived earlier, W for Fermi-Dirac corresponding to the distribution set Ni. These were the notations that we are used. We obtained it. This is equal to some pi over I product of, okay, so I can take it like this, gi factorial divided by ni factorial into gi minus ni factorial. So this was equation number 8 that we have derived in the previous or penultimate lecture. So let me call this one as equation number 1 for the time being. Okay, so this equation was, you were asked to memorize this equation, which were borrowed from basic combinations theory, NCR equation. Okay, now you know what to do. We have to take log of W. Therefore, the same procedure, we have to find out the most probable distribution. So for that we have to maximize log of W. So log of W will be equal to, here there is, directly you can do that. When you take log of the right side, product will become summation as usual, sum over I log of, so log A by B is log A minus log B. So in the denominator I'll be using the summation also. So log gi factorial, numerator log gi factorial minus, see what we, the denominator will be, the product will be converted into a sum, that is by log ni factorial, plus will become minus when you open the bracket, so minus log of gi minus ni factorial. Now you know what to do. You have to expand by using Stirling's approximation, so that is equal to sum over I. Same strategy that we have adopted in the Bose-Einstein distribution derivation, gi log gi minus gi, that is the first one, minus, what will be the next thing? That will be ni log ni, minus ni will become plus ni directly, then minus bracket gi minus ni log of gi minus ni, then there was a minus and minus will become plus, so that is plus gi, and that minus term plus term will become minus to some minus ni. So that is what we are going to get to finally, right? So now there are some chances of getting cancellation. There is a plus ni here, there is a minus ni here getting cancelled, gi plus gi here, minus gi here getting cancelled away. So what you are left with, you can rearrange. Okay, so you can take common terms here. Similar thing we have done in the previous case also. So I am rearranging it. So that is sum over I, taking common terms and rearranging, ni log gi minus ni. Okay, so ni log gi minus ni, I'm writing like this, divided by ni. Okay, so that is log a minus b equal to log a by b. That is what we are using, minus gi into, first I have taken this one, see ni, this minus and this minus has become plus, so that is why I have got the first term. Then second term will be minus gi log of gi minus ni divided by gi. Okay, so you note it here, it is gi minus ni by ni here it is gi minus ni by gi here, multiplied by the two corresponding terms over there. So which can be again modified following the same steps that you have done previously, that is sum over I. We can write this one as ni log, what is that one, gi by ni minus 1, gi by ni minus 1, separating out, then minus gi log Okay, 1 minus ni by gi, 1 minus ni by gi. Okay, so this is let me call this is equation number 2. Now let us take the differential of this one to get it maximized. Therefore delta of log w, for that you have to take the product rule and all. So I'm just doing it directly without much explanation. Sum over I, we have done the similar things. Remember here only ni is variable, gi is fixed. Okay, gi is the number of levels, as I told you. Ni is the number of particles in the ith level, which can vary depending on the distribution. So ni is a variable, so I'm treating ni into, so in the second factor also there is an ni term, so I have to take that thing. So log in the for the log it will be 1 by gi by ni minus 1 into, then I have to take that of the gi by ni, that will be into minus gi by ni square delta ni, that is for first thing, plus product rule, that is delta ni into second term as such, that is log of gi by ni minus 1. So for the first term it is over. Similarly for the second term it's quite simple, but minus gi into, because g is a constant. For the log of okay, quantity, it will be 1 by 1 minus ni by gi into, what is that, into minus just delta ni by gi. That is the, you know that this gi and this gi will be getting cancelled, as we have done in the previous example, and here there is one ni getting cancelled with one ni square here. So you can see here every term delta ni is common, so delta ni is common in all the three terms, which can be taken outside. This minus and minus will become plus. So I'm rewriting so the same repetition of same stuff that we have done there. So that is delta of log w, delta of log w will be equal to sum over I minus gi by ni. You can just verify this one, divided by in the denominator there was gi by ni minus 1, then plus okay, log plus log gi by ni minus 1, then plus 1 divided by 1 minus ni by gi. Okay, so whole multiplied by delta ni taken as common factor. So this is the thing that we have got, right? So, and you know what you have to do next, what you have to do, you can just take this term to the denominator. So it will become what, gi by ni will be getting cancelled, so there is a minus sign. So it will become, okay, it will be getting inverted. So 1 by gi by ni is ni by gi. So you will get this term as what, just the thing. So this term and this term will be same with the signs reverse, so they will be getting okay, what is that, cancelled away. So what you're left with here is simply sum over I of the second term only, log of gi by ni minus 1. This is what we are into delta ni, of course. Let me call this one as equation number 3 as usual. Now for the most probable distribution, you know, for the most, that is our aim finally, most probable distribution, we can call it as ni star, delta of log w should be equal to 0. Okay, and using Lagrange's method, for since the constraints are to be included, Lagrange's method of undetermined multipliers, we can write that the delta log w for the maximization, delta log w, which is to be set equal to 0, minus alpha into, I'm bringing in the constraints, sum over I delta ni minus beta into sum over I ei delta ni must be equated to 0. Okay, so that is my fourth relevant step. Now you can substitute for log w, delta log w from equation number 3. So equation number 4 becomes sum over I. You can take sum over I, and delta ni is also common. So I can write log of gi by ni minus 1, then minus alpha minus beta ei. Okay, summation and delta ni are taken common terms, so that is equal to 0. Same steps that we have followed. And since it is correspond to the most probable distribution set ni star, let me make ni here as ni star. Now you know what to do. So since delta ni is arbitrary, for this equation to be correct for any arbitrary value of delta ni, the quantity, this quantity in this bracket should be summarily or identically equal to 0. So it says that okay, log of gi by ni star, okay, minus 1, that should be equal to, okay, alpha plus beta ei, no differences. Or I can get rid of the logarithm, that is gi by ni star, okay, minus 1 will be equal to e raised to alpha plus beta ei, or gi by ni star will be equal to I can take e raised to alpha plus beta ei minus 1 on going to the other side become plus 1, right? But you know that we are interested in ni star by gi, number of particles per level, or the mean occupation number is what we are okay, looking for. So therefore I can write that, okay, ni star, I'm trying to do it here itself, ni star by gi for this particular case. I can write, this is for which case? This is for the Fermi Dirac case, that is equal to the reciprocal of the right side, that is 1 divided by e raised to alpha plus beta ei plus 1, okay, plus 1. And this quantity is what we are defining as f of ei for the Fermi Dirac case. And this is an equation that's worth remembering. This is the equation that is worth remembering, and we call this equation, final equation, as what is known as the Fermi Dirac distribution function. So this is known as the Fermi Dirac distribution function. So it gives you an idea about how the fermions will be getting distributed in the available energy levels, obeying the Pauli exclusion principle. Okay, so and this gives you the mean occupation number. It's also known as or mean occupation number. That's a physical meaning actually of this distribution function, mean occupation number. So it's also denoted as NFD. Similarly, the earlier equation for Bose-Einstein, it is written as NBE. So mean occupation number. That's the thing. Now one thing is quite notable here. You can see that the denominator has got a plus 1. Okay, so when you compare this case with what the previous case, so I'll be write that one, f of fd of ei is obtained to be equal to 1 divided by e raised to alpha plus beta ei plus 1. Okay, whereas f of be for okay, no, of function ei for Bose-Einstein system was obtained as same thing for comparison, e raised to alpha plus beta ei minus 1. So please note that there is a plus 1 here. Okay, it's a plus 1 here and there is a minus 1. So you can see that this f, which function will be, remember, see, this is nothing but the mean occupation number, that is ni star divided by gi, or it is nothing but denoted as see, mean value, sorry, okay, it can be also denoted as mean occupation number for Fermi Dirac case. This is also the sorry, this is FD case, and this is also ni star by gi, but for the Bose-Einstein's case. So this is the mean occupation number for Bose-Einstein's state. Now you know that due to the presence of plus, okay, and minus ones over in the denominator, which one will be greater? Okay, if you just make a comparison, which occupation number will be greater? Certainly you can see that see the mean occupation number for Bose-Einstein case, because there is a denominator is minus 1, so denominator is lesser, okay, compared to the other one there. So that is what greater than the mean occupation number for a Fermi Dirac case. The reason also physically you can understand, because you know, in the case of Fermi Dirac, since the particles has to obey the Pauli exclusion principle, there cannot be accumulation of particles in the same level. Okay, whereas there is no such a restriction for bosons. ബോസോൺസിന് ഒരു ലെവലിൽ എത്ര പാർട്ടിക്കിൾസ് വേണമെങ്കിലും ഇങ്ങനെ അക്യുമുലേറ്റ് ചെയ്തുകൊണ്ടിരിക്കാം. എന്നാൽ പോളി എക്സ്ക്ലൂഷൻ പ്രിൻസിപ്പിൾ പ്രകാരം ഒരേ ലെവലിലുള്ള അക്യുമുലേഷൻ പോസിബിൾ അല്ലാത്തതുകൊണ്ട് ഒരു ലെവലിൻ്റെ മീൻ ഒക്യുപ്പേഷൻ നമ്പർ എന്ന് പറയുന്നത് എപ്പോഴും എന്തായിരിക്കും, 1-നേക്കാളും കുറവായിരിക്കും. ഓക്കെ, മാക്സിമം വാല്യൂ 1 ആണ്. ഒന്നുകിൽ ഒരു ലെവൽ ഒക്യുപ്പൈഡ് ആവാം, ഒരു പാർട്ടിക്കിൾ കൊണ്ട് ഒക്യുപ്പൈഡ് ആവാം, അല്ലെങ്കിൽ ലെവൽ അൺഒക്യുപ്പൈഡ് ആവാം. അപ്പോൾ അൺഒക്യുപ്പൈഡ് ലെവലുകൾ നമ്മുടെ സെല്ലിൻ്റെ ഉള്ളിലുണ്ടെങ്കിൽ തീർച്ചയായിട്ടും മീൻ ഒക്യുപ്പേഷൻ നമ്പർ 1-നേക്കാളും കുറവാകും. മാക്സിമം വാല്യൂ ഓഫ് മീൻ ഒക്യുപ്പേഷൻ നമ്പർ ഫോർ എ ഫെർമി ഡിറാക് സിസ്റ്റം വിൽ ബി ഈക്വൽ ടു 1. എന്നാൽ ബോസ്-ഐൻസ്റ്റൈൻ സ്റ്റേറ്റ്സിൽ അങ്ങനെ ഒരു റെസ്ട്രിക്ഷൻ ഇല്ല. ഒരു ലെവലിൽ എത്ര ബോസോൺസ് വേണമെങ്കിലും ഒക്യുപ്പൈഡ് ആവാം. അപ്പോൾ ആ ഒരു ഡിഫറൻസ് ഉണ്ട്. ആ ഡിഫറൻസ് കാരണമാണ് ഈ മൈനസും പ്ലസും ഓർത്തിരിക്കുക. സോ പ്ലീസ് റിമെമ്പർ ദ പ്ലസ് ആൻഡ് മൈനസ്. സോ വേണമെങ്കിൽ നമുക്ക് ഈ രണ്ടെണ്ണത്തിനെയും കൂടെ ഒരുമിച്ച് ചേർത്തുകൊണ്ട് ഒരു ഒറ്റ ഡിസ്ട്രിബ്യൂഷൻ ഫംഗ്ഷൻ ആയിട്ട് പഠിക്കാൻ പറ്റും. എങ്ങനെയാണ്? എഫ് ഓഫ് ഇ ഐ ഈസ് ഈക്വൽ ടു എന്ന് പറഞ്ഞ് എഴുതിയിട്ട് 1 ഡിവൈഡഡ് ബൈ ഇ റേസ് ടു ആൽഫ പ്ലസ് ബീറ്റ ഇ ഐ പ്ലസ് ഓർ മൈനസ് 1 എന്ന് എഴുതിയാൽ മതി. ഓക്കെ, സോ വേർ ദ പ്ലസ് കേസ് ഈസ് ഫോർ വിച്ച് വൺ? പ്ലസ് കേസ് ഈസ് ഫോർ ഫെർമി ഡിറാക് എന്ന് ഓർത്തോണം. ഓക്കെ, പ്ലസ് ഈസ് ഫോർ ഫെർമി ഡിറാക് ആൻഡ് മൈനസ് ഈസ് ഫോർ ഫെർമി ഡിറാക്കിന് പ്ലസ് ആണ്, കാരണം അത് കുറയണം. ഡിനോമിനേറ്റർ കൂടുമ്പോഴാണ് ടോട്ടൽ വാല്യൂ കുറയുക. ബോസ്-ഐൻസ്റ്റൈനിന് -1 ആണ് എന്നുള്ള കാര്യം ഓർത്തിരിക്കുക. ഓക്കെ, ഓർ ഇങ്ങനെ എഴുതാൻ +1 ഫോർ ഫെർമി ഡിറാക് ആൻഡ് -1 ഫോർ Bose-Einstein case. So this gives you the Fermi-Dirac distribution and Bose-Einstein distribution functions. Okay, thank you.